I started putting this stuff.
Yeah, it's from the back.
I think back then, it was really bad to go into these. That one paragraph, I was just gonna take all the photos.
Yes.
Go to this.
Yeah, I mean, I wasn't sure.
So I'm ready. We can quiet down. Hello? Okay. So we're just going to get started on this lecture. We will finish it on Wednesday, but this lecture will be largely just helping you prepare for Lab 2. And part of Lab 2 is now you'll need to know how to represent numbers in VHDL because you'll be assigning them. So there are multiple bases supported. I'm going to give you examples for binary, octal, hex, and decimal. We all know these formats already, yes? All right, so binary. If I want a 4-bit binary number, I just put the 4 bits in quotations, and I can assign that to a signal. So this is hex F. Decimal, what is this? 1111.
15.
Yes, 15, right? So octal. So octal is how many equivalent binary bits? So it's base 8. So, but how many equivalent binary bits for one base 8 number?
4.
So that's equivalent to hex. It's 3 bits, right? So this is base 8, so it's 8 times 3, right? So what is 8 times 3? 24 plus 7, right? So this is 31. Right? And if I wanted to convert this to binary, my 3 bits that make 3 are 0, 1, 1, and then 1, 1, 1 makes 7, right? So hex, you pre-append an X instead of an O. And then you have the quotations again, and now you're just putting hex numbers here. So AA, so this is 16 times what? What is A? A is 10, 10, 10. So 16 times 10, 160 plus 10, right? So this is 170. Right? And then you can just use decimal numbers like this if you wanted to create 15 or say negative 32. The only thing about decimal numbers is that what it will do is create a 32-bit representation of this number. And if you are trying to assign it to, say, a 8-bit signal, it will only assign the last 8 bits. And it'll just throw away the upper bits. So this is fine for most cases, right? But if you are trying to assign a number that is larger than the representation available by those 8 bits, it's going to be cut off. So you have to be careful if you're doing this. But you can explicitly assign all of the bits and match the bit width with this representation. Right? Like if I needed 5 bits, I would just put a 0 in front here. Right? Whereas if I did the assignment as 15, sure, it's all zeros in front and it doesn't matter because they will just get chopped off. But that's not always the case. Like if I wanted to assign 16 to a 4-bit number, I actually get 0. And you would see that in the waveform. So are we all good with these representations, how to use them? Okay. So here's our example of mismatch sizes. So here we have a standard logic vector, 8 bits, right? 7 down to 0. So 8-bit vector. And we want to assign 10 to it, but we have this binary representation and then this hexadecimal representation. And we can concatenate them together with the AND operator. So I get 4 zeros and then 1 0 1 0. And that would be assigned to the 8 bits of this signal counter. So this is how you can combine and concatenate bit strings together. Make sense? I don't see a single nodding head. Makes sense? Okay, question. Yes, this is 1 0 1 0. Because this is hex, so A is 10. So the 4-bit binary representation of 10 is 1 0 1 0. 8 plus 2. Yeah. Any other question? Okay. So again, if you are trying to assign mismatching sizes, it's going to require you to do this. So if standard logic vector was 6 down to 0, you would just remove one of these zeros. Okay. So this is your first checkpoint, and I think it's probably the only one that we'll get through for today. Your code is 710. So again, do this on your own first. Okay, so I think most of you guys are done working on this, and I'm looking at the results. We're a little bit under the threshold, so do talk to the people around you. Make sure you select the most correct answer. Huh? What's the typo? That's not the typo. It's not the. That's not what I'm trying to get at.
Okay, I'll change my answer. I haven't done this, the previous slide was like, wait. Yes.
I did it. Yeah, you want to make them because we could have. They know. Space and true. That's what's really
Change your answer if you were convinced to change your answer. Okay, I hear discussion diverging. Somehow we went backwards. So let's go over this together. Yeah, so it is D.
It is.
Yeah. So remember, we need to match the bit width, right? So here out is the 5 bits representing 10, right? So this is correct. This one, the bit width does not match. You're trying to assign 4 bits to 5 bits. It will complain to you. So this doesn't work. And then here, we have 4 bits that represent 10, right? And we're concatenating a 0 to make it 5 bits. Yes.
Is there a normal decimal like 1 to 10? This is like
Yeah, so you could also do 10, but like this says, you may encounter some problems doing
how
this.
do you know that's
Oh, because if you put it in quotations, it's binary. Right?
okay.
So quotations like this, binary, no quotations, decimal. Octal, you pre-append as an O. Hex, you pre-append an X before you put the quotations. That's how you know it's the different representations. Question.
So it's 8 only.
Yes, A is 10. If you're hex, A is a 10. B is 11. C is 12. All the way up to F, which is 15. Okay, so are we clear with this one, why it's D? Because A and B both work. So I think my hint strayed many of you to E, because it went from 0% answering E to 14% answering E. All right, so one thing that we should discuss is overflow with your binary representations. So with a fixed representation, you have a fixed range of numbers that you can represent. And if you overflow, you're not going to get the correct answer. You'll get a smaller number than intended, or maybe a larger number is intended if you're signed. Right, so here, assuming we have 4-bit 2's complement numbers, so these are signed numbers, we can detect overflow by detecting when the 2 numbers, signed bits, are the same, but are different from the results, signed bits. Right, because if the 2 numbers, signed bits, are different, overflow is impossible for adding a positive number with a negative number with the same representation, same 4 bits. Right, I can't get outside of the range. Correct? But if they are the same sign, so here, this is a positive number, right? This is a positive number. We see this? And this is 7. This is 1. When I add them, I should get 8. But instead, I get -1. Do we all know why this is -1? Yes. Is anyone confused why this is -1? I can explain. Okay. So the way that we know that this is -1 is because we are 2's complement. So like you mentioned, the most significant bit tells us that it's negative because it's 1. And then to convert it to its positive form so we can figure out what the actual number is, we flip all of these bits. So this becomes 0. Oh wait, I'm sorry, this was not -1. So we flip all of these bits. So this is 0, 1, 1, 1. And then we add 1 to it. So this becomes 0, carry the 1 over. This is 0, carry the 1 over. This is 0, carry the 1 over. So it's actually -8. So sorry I misspoke, but it's -8, which is not 8, right? So we have overflow here. And again, like it states here, you can detect overflow by looking at the sign bits. And then if the resulting sign bit is different, I'm adding 2 positive numbers, right? Surely I cannot get a negative number.
But is getting that answer not so correct? 'Cause that does, like, 1000 is 8, so.
Yeah, but you're expecting another 4-bit 2's complement number. So I'm treating this as -8 and the output. Right? Right, so same thing, 2 negative numbers. How am I getting a positive number, right? So this is when you know that there's overflow. And then here again, we have a negative number and we're adding a positive number. So we know that there's no overflow possible. So we just need to check overflow if the sign bits are the same. Yes.
And if it's positive, adding a negative, it's also.
Yeah, it's impossible. Because in order to get to overflow, I have to go outside of the range. So if I have a positive number that's in the range, I'm adding a negative number that's also in the range, I can only move within the range. I would have to have a negative number that is larger than my range to offset the positive and then also get it outside of the negative range. But if they're both in the same range, I can't leave that range, right? Okay, so here is the other method, which is more efficient than checking the sign bits. So we can just detect the difference between the carry in to the sign bits and the carry out. So our overflow equation would just become the XOR between the most significant carry in and the carry out. So this is the same examples from before, and we can see our carries here, and then the most significant carry. I take the XOR of this with the carry out, which is 0. XOR of this is 1, so there's overflow. We see this? Are you guys alive? Does quiz kill you? What happened? Will we see how the XOR is working here? Yes? No? Question? Okay. So we're just trying to detect overflow in a more simple and efficient way. And I'm stating that if we take the XOR between the most significant carry in or carry with the carry out, that will tell us if there's overflow, if the result of the XOR is 1. So when we add these two numbers together, right? So 1 plus 1, 0, carry. 1 plus 1, 0, carry. 1 plus 1, 0, carry. This is my most significant carry, right? So this is C3. And then 1 plus 0 gives me 1. So my carry out, or C4, is 0, because there is no carry. And I take the XOR of C3 and C4, the result of 0 XOR 1 is 1, right? So that means there's overflow. Rather than checking the sign bits here and checking that with this. So same thing here. I'm not going to go through the math on this one, but we see the most significant carry and the carry out, XOR them. It gives you 1 again. So this is also overflow. And then here, most significant carry, the carry out, the XOR of this is 0. So there's no overflow. Is this better? Okay. So then we want to go into how to do subtraction with the same hardware. So I'm just going to briefly describe this because we are out of time. But if I want to do A minus B, I can just do A plus negative B, right? So that's the basis of using the same exact adder to implement adder and subtractor. All right, so we'll continue these slides on Wednesday.
Just a negative B is the two's complement of the.
So we have to track all those carries.
You're going to generate the carries in order to implement the hardware.
Oh, okay.
So then in the end, you just need to add the XOR gate.